Well, hello and good evening. Very warm welcome to our live Plumtree meeting for June. Hope you're all keeping well. This evening we've got a number of speakers lined up and we're joined by not one but two BA section directors, so more on them shortly. So our main topic for tonight is going to be on Noctilucent Clouds, and if you've been up in the early hours, you'll know that's very appropriate at the moment because we've had a great display of those over the last week or so with the clear skies. So James Dawson and Sandra Brantingham are going to talk all things Noctilucent Clouds to us shortly. But before we do, I'm pleased to say that we're joined by the Variable Stars Section Director from the British Astronomical Association, Jeremy Shears. So very good evening, Jeremy. And Jeremy's going to talk to us tonight on the bright nova that's recently appeared in Hercules. So a very warm welcome back to Nottingham Astronomical Society, Jeremy. Hope you're well.
All well here, thank you. I'm going to share my screen, Richard.
Yeah, you should be able to do that
so,
now.
Yeah, let me know when you can see it. And I'll put it into slideshare mode.
That's perfect. Yep, let's hear the latest on the nova then.
Excellent. I'll just get my little laser pointer going. Yeah, thanks for inviting me this evening, Richard. Great to be with you at Nottingham Astro once again. It's actually been a pretty exciting week in the variable star realms because we have this nova discovered in Hercules. So I want to tell you a little bit about it. It was actually discovered last Saturday at 2 o'clock in the afternoon our time by a Japanese amateur astronomer who specializes in trying to detect novae as soon as they appear in the night sky. And it's interesting to see that he uses pretty standard domestic equipment, a Canon EOS camera and a telephoto lens. And he goes out night after night trying to spot these novae. And he saw one 2 o'clock our time on Saturday afternoon, posted it to the Central Bureau of Astronomical Telegrams imminent discovery page. And then an alert went out. And I picked that up at just after 5 o'clock Saturday afternoon. Just got home from a lovely day out. And shortly after that, sent an alert out to BAA members because although he discovered it at 2 o'clock at magnitude 8, by the time the alert was issued, it'd been picked up at magnitude 6.4 by an observer in Australia. So it was clearly brightening. And I was keen to get as many people observing this as possible. So as you will know, it gets dark pretty late here at the moment. So I had to wait up until well after 11 o'clock at night to be able to spot the nova myself at about magnitude 6.3. I used binoculars, just a small pair of binoculars. And it was fairly easy to find. So I was pretty excited and put my observations out onto the internet. A lot of other people saw it that night. It was clear over much of the country. And here's the light curve that we've had since. So you can see it was almost naked eye visibility when it was discovered, just below magnitude 6. And then it faded very, very quickly. And this is what's remarkable about this nova. It's probably the fastest fading nova on record. It faded 3 magnitudes in just over 2 days. And that's far faster than any other nova. So that's exciting in its own right, but it's a bit disappointing because it's also got really faint quite quickly. I've just seen observations coming in from Australia earlier this afternoon at around magnitude 10.2. So you can see how it's faded. The light curve here shows 2 kinds of observations. The green ones are with CCDs, and the open circles are with visual observations, initially with binoculars and then with telescopes. So if you do want to go out and see it, it's fairly easy to find. As soon as it gets dark, this is a plot for midnight tonight. Look southeast. First of all, you'll be able to see the summer triangle of Vega, Deneb, and Altair coming into view. And I've got a circle here that shows where the nova is. Although it's nova in Hercules, it's actually just close to the border with Aquila, the Eagle. So that's where to find it. You can find charts online via the BAA website if you want to know more details about it. Just show you a couple of pictures. This is a photograph taken during the week by Mazin Yunus in Manchester. using an 8-inch reflector. You can see that the nova is quite red there. People have said it's very red visually if they look through a sort of a 10-inch, 12-inch telescope. I can see it as just slightly red in a 4-inch refractor. It's in a lovely rich star field. Most novae occur in the Milky Way because that's where most stars are, and a nova is, as we're coming on to in a moment, an eruption of a binary star. What Mazin did was to superimpose his picture of the bright nova here with an image taken by professionals at another time, and you can see how brightly that star appears. The star before was fainter than 20th magnitude. I don't think anybody's actually identified the definitive precursor star. So it's brightened 14 magnitudes within a few hours, which is really quite remarkable. Just briefly, what is a nova? It's a binary star system. There's an artist's impression here. So you'll have a very small white dwarf star, which is being orbited by usually a red dwarf. So the red dwarf is going around, and because of the strong magnetic pull of the white dwarf, it's sucking hydrogen off the red dwarf, and that spirals through this accretion disk onto the white dwarf. And with time, material builds up, hydrogen builds up on the surface of the white dwarf until it reaches such a density, there's a runaway thermonuclear reaction. And that's what causes the nova reaction, eruption, which I'll show in the next slide. This is, again, an artist's impression. You can see the disk and the secondary star on the right, and then the explosion of the material coming out. It doesn't destroy the double star, so the white dwarf and the red dwarf will remain there, but it will leave this cloud of gas, which may become invisible in the future as a planetary nebula. So that's what's happening astrophysically. In the early days, in the early hours of Sunday morning, people were keen to find out whether this was a nova or some other phenomenon, and therefore people were looking for the definitive signature in the spectrum. And this includes amateurs. Amateurs are getting very good at this these days. This is by BAA member Hugh Allen. And I won't go into all the details, but essentially you can see you can see a number of peaks here where I've just highlighted. And those are peaks caused by excited hydrogen. So these are called emission lines. So they're brighter lines, and you can see them in the coloured spectrum below. And that you can see the bright red band there. That's hydrogen. Excuse me. That's hydrogen alpha, and that's why in the photograph I showed earlier, the star looks a bit red. So that's the excited hydrogen caused by the eruption. But next to it, and this is the giveaway, there is a dip. This is an absorption band, also caused by hydrogen. And this signature here is called a P Cygni profile, and that's diagnostic of a nova explosion. You may ask, why is the wavelength different? Well, the reason is that the gas is expanding, in this case, towards us. You can imagine the gas coming towards us. So it's slightly it's slightly blue shifted. So the absorption is blue shifted by around 75 angstroms. And using a simple relationship between velocity and that redshift or blue shift in this case, you can work out that the gas was expanding at around 3,500 kilometers a second. So pretty fast. So exciting times. Do go out and have a look at it if you get a chance. I haven't got any details with me, but there is another nova around that you might want to look up on the internet or on the BAA website, which is Nova Cassiopeia. That's around 7th magnitude, so it's brighter. That erupted at in the middle of March to 6th magnitude again, and it's still around. So that's a slow nova. And that's probably going to be around for weeks, if not months to come. Whereas Nova Hercules, it's almost gone. So grab your opportunities. I'll stop there.
Brilliant. Thank you very much indeed, Jeremy, for that. That's interesting stuff. I guess we had quite decent weather other than the day of the eclipse. So have you had quite a few observations in? It's
been a good month so far. In fact, I was just putting in my solar observations for today. I do solar prominence counts, and What are we today? Is it no? It's the 16th today.
17th.
17th today. I've only missed one day so far due to cloud in June, so it's been pretty good. Trouble is, it gets dark so darn late these days, and the nights are short.
Does, but yeah. Well, thanks very much for doing that. I've been told we've got to take questions at the end because we're pushed for time. So, any questions for Jeremy? Are you happy to stick around, and we'll take those once the
I'll be here.
Talk on Noctilucent Clouds is over.
Yep.
So,
looking forward to
that. Yeah, Jeremy can have a look at those if you want to put them in now, and we'll pick those up at the end. So, let's push on because it's 10 past. Oh, just gone 10 past already. So, our main talk tonight is on Noctilucent Clouds. So let's crack on with that with James and Sandra.
Right. Am I audible?
Yep.
That's good. So hello. I don't know where to look at. I've got too many screens. James Dawson here in West Bridgford. Looking out the window, it's very cloudy. No chance of seeing anything tonight other than cloud. And so we're going to talk about Noctilucent Clouds. And when I click the right screen, I'm here. I've got a glamorous assistant in the form of Sandra Brantingham, who's the section director for the BAA on Aurora and Noctilucent Clouds. Say hello, Sandra. I think you're on mute, Sandra. No, can't hear you. Turn it off and on and again. Richard, can you help with
How's that?
Oh, that's better.
Yeah, slight problem this end.
Fine.
Right.
Tell us where you are in the world,
everybody.
Sandra.
Right, basically I'm just short of the Moray coast, about 8 miles from the Moray coast. My left is Inverness, to my right is Aberdeen.
Right.
We've just had a massive rainstorm go through, but there's patches of blue sky, so
Okay.
I'm hopeful.
Okay. Right,
I'm well clear of the mud anyway.
So Sandra, do chip in because you'll know a lot more about this clearly than I do. But hopefully it's a take on Noctilucent Clouds. So these are seemingly luminous clouds seen after sunset. They're usually low to the northern horizon, and they're observed in the summer months. I thought I'd change that slide. So for the UK, Northern Hemisphere, that's sort of middle of May to middle of August. And in the Southern Hemisphere, it's their summer. So it's November to February. Is that about right?
Correct. Yeah, that's it. Yeah.
And we'll talk about why their summer month features later. Now, they're typically only observed in a relatively narrow band of the globe, usually about 50 to 65 degrees north and south of the equator. And on this map here, I've put where these bands are. This is roughly, don't hold me to absolute accuracy for this, but the UK sits pretty much bang in the center. And then we've got this band at the in the southern hemisphere as well. And you can see there aren't many land masses which fall, which is why there are many fewer observations from the southern hemisphere.
Just a pointer. All right, just hold that slide. The problem with viewing any further north than about where the top of the UK is, it gets so light you can't see a thing. So basically, and also for some reason, and we're not sure why, it's spreading south, and we're seeing how far it'll go. But last year it was picked up in Italy, so we don't know why it's spreading. So something that's why your observations are important. So
okay. So here's a picture I took of some Noctilucent Clouds 2 summers ago from the observatory, and this is just a 1 second exposure on my Canon, and you can see these sort of bright clouds in the distance, very low to the horizon, and this is looking north, and you can see the lower sort of atmospheric clouds, which are dark and not illuminated by the sun. So
that's a lovely shot. Just a point. Do you notice they're red as well? That's very rare. Now that's caused by, we think it's coming through the atmosphere, so it's actually catching the top of the atmosphere. But it's very rare to actually see red noctilucent clouds.
Right.
So that's an excellent shot.
I'd heard some cirrus clouds can be illuminated by light pollution and give a sort of orange glow and confuse some people that they're noctilucents.
Oh yes, yeah, and you've got to be very careful. So, but normally you get the same impression with the aurora, i.e., you've got dark clouds in the bottom, and the cirrus
Right.
clouds normally look dark. But and you can also get moonlight as well. So
yeah. So a bit of the history of noctilucent clouds. So we have to go to 1883 to start with, when Krakatoa had a major eruption in Indonesia. This was a massive explosion, equivalent to, they think, about 200 megatons of TNT, ejected a tremendous amount of rock. And they say it was heard 4,000 kilometers away, and well over 36,000 people died from this. Now, I can't remember if I shared with sound, so we might not get sound with this, but this is a video, and here you're going to see a explosion of a volcano, and look above the volcano at the impact on the atmosphere. Do you get sound or not?
I'm not.
No, I've pressed the wrong button. I'm sorry. So the volcano is going to go, and look at the shockwave above. You see the clouds condensing. And
there it goes.
The chap holding the camera gets hit by the shockwave, and that was the shockwave. And it's very loud. So you're probably grateful you didn't have the sound on that. So when Krakatoa went, there was a tremendous amount of dust in the atmosphere, and it caused vivid sunsets and sunrises for many months afterwards. And this was about the time which Edvard Munch painted The Scream. And there's people wonder if this sunset in the background here was part of the Krakatoa event. So the first suggestion of noctilucent clouds in any published literature, I've actually found this letter, Sandra, from 1884, a year before Backhouse, and this is talking again about the sunsets. And Robert Leslie says the sky around and above where the sun had set looking almost ceiling-like in its opacity, upon which soon appears numbers of weird small cloud forms, at times very regular, like ripple marks in sand, or the bones of some great fish or saurian embedded on a slab of stone. Now, do you think
that's a perfect description of noctilucent clouds?
Yeah, that's what I think.
Yes, without a shadow of a doubt. That rippley sand effect, patchy like, that's its hallmark.
Yeah.
So yes, agreed.
So I do think Robert Leslie probably was the first to publish in 1884 in Nature. And then again in Nature the following year, Robert Leslie again writes and is commenting about these clouds. And in response to this, Thomas Backhouse publishes in the Meteorological magazine, and says he first saw these clouds in early June, whilst he was in June 1885, whilst he was in Germany. And Backhouse is usually the person who's credited with making an observation of these clouds first. Various people picked up on this, and people became interested in this. And this Otto Jesse was the first to photograph noctilucent clouds. The end of the 1800s, photography is really picking up. And these are some pictures actually from 1889. And you can see these white stripes So this is after sunset, and the images won't be as good as modern digital images, but they do clearly show there's something there above the horizon after sunset. And photographs were used to triangulate the clouds and work out the altitude, and the altitude was calculated to be sort of 82 kilometers above sea level. And they also looked at the speed of cloud movement. And you can see there they're moving quite rapidly, both in east-west direction and a north-south. So we're going to pause with the history and do some meteorology. So this is a plot of altitude above sea level and temperature at those various altitudes. And what you can see is the temperature drops and then rises and drops and then rises again. And in anesthesia, we call these inflection points. I don't know if they're inflection points anywhere else when we use ventilators. Are they called inflection points, Sandra? Have you ever heard that?
I'm not sure.
Julian,
that's a new one of me.
Yeah, Julian's saying yes. So in astrophysics, they must be inflection points. So these inflection points mark a change in something. And this is where we get the terms for the levels of the atmosphere. And so here's another plot showing the different levels of our atmosphere. The troposphere is where most of our weather happens and where we live. The stratosphere is above, the mesosphere and the thermosphere. We're going to quickly look at the thermosphere. So if we go back here, the mesosphere sort of ends at about 80 kilometers above sea level, and that's here. And then the thermosphere goes up, and here's the International Space Station at 400 kilometers above sea level. And above the thermosphere is the exosphere, and the exosphere kind of merges with space. So there's not a clear boundary between the Earth's atmosphere and space. The exosphere sort of is that gradient between the two. And depending on the solar wind, the pressure of the solar wind, the exosphere and the thermosphere can compress and expand. So they're not fixed boundaries. So thinking a bit about Earth satellites, satellites are generally either in low Earth orbit, medium Earth orbit, or high Earth orbit. And we've got some measurements there. Again, anyone can have the slides if they want to look at these in more detail. And so we've got some low Earth orbit satellites, medium and then high. So the ISS and the Hubble are low Earth orbit satellites. GPS satellites are generally medium Earth orbit. And then the geostationary satellites, which go just around the equator, are high Earth orbit. And obviously the moon is very high. There's some distances there. So back to our plot of the layers of the atmosphere. So in the troposphere, we've got, this is where aircraft fly, generally under 12 kilometers, although I've written it down, the Lockheed U-2 in the 50s could get up to 21 kilometers. I remember because it was the other way to 12. So the Lockheed U-2, my memory's awful, is somewhere up here. Weather balloons generally can get up to 18 to 37 kilometers, but some have got much higher. The ozone layer sits in the stratosphere. And when I went over these slides with Sandra the other day, she telling me that the ozone layer is the reason the stratosphere heats up again. Is it absorbing the solar radiation and kind of re-emitting it into that layer?
Basically, yes.
Right.
Yeah, it's a bit more complicated, but basically, yes, that's what causes the heat there.
Okay.
It also protects us.
Yeah.
As we found out.
Yeah. Here we've got a meteor coming into the Earth's atmosphere, and it's burning up in the thermosphere. And we're going to talk a bit more about what happens to the little bits of things which are left from meteors burning up. And here we've got my interpretation in PowerPoint of an aurora. And this is happening again at the junction between the thermosphere and the mesosphere. I know nothing about aurora, Sandra, so do you want to say anything about these here, or should we save that?
I'll just give you a quick one. Basically, it starts at about 80 kilometers or 50 miles and then goes up to about 150 miles.
Right.
And the reason for that is the density of the atmosphere. If you can imagine, the aurora is just vibration, creates its own light. Lower down, and the electrons do get lower down, but the atmosphere is too dense. If you think of it, of the three bears and the porridge, it's just right at the top of the mesosphere into the thermosphere. It's too hot or too dense down the bottom, and it's too cold up the top. So, or too far apart. So basically, that's why you see the aurora there.
Do you like my PowerPoint representation of the aurora?
Absolutely. Very impressive.
And then between the mesosphere and the thermosphere, in fact, between all the layers, there's the interval, or the junction of the
Top
two
edge.
are called, the top edge are called pauses. So we've got the tropopause, and this is at the top of the mesosphere, we've got the mesopause, and this is where our noctilucent clouds are forming. So we go.
If you go to your temperature graph, because it actually shows why it's the coldest part. It can't go any higher. If you remember the London smogs, they used to stop because there was hot air going over the top and they couldn't go any higher. It's exactly the same reason.
Right.
It can't go above that 80-kilometer mark.
Right. Interesting. So here we've got, again, labeling of these layers. And on this plot, we've also got a representation of the pressure at these various altitudes. You can see down at Earth, we've got atmospheric pressure, and then in a linear, I don't know if it's not linear, but as it drops, it becomes negligible in the mesosphere, and then remains negligible as the number of particles decreases. And then here we've got water vapor. Again, ambient sort of humidity, and then as you get higher and higher, the amount of water per unit volume of gas reduces. Now, so this is the layer we're interested in for the noctilucent clouds, the mesosphere, and really the mesopause, this space at the top of the mesosphere. Now, thinking about the temperature in the mesosphere, or the mesopause, it's not fixed throughout the year. It does vary. And what this plot is showing, this is days of the year numbered 0 to 365 along the x-axis, and then up the y-axis we've got temperature in Kelvin. I've asked permission of this Patrick Espley chap, and he's happy I use his plot. And I've added in centigrade on the right. And you can see this is for Northern Hemisphere in our late winter and spring. In fact, let me change slides. The average temperature is about -60. In our summer, the temperature drops and we get an average temperature of about -100. And then again, autumn and early winter, the temperature warms up again to -60. And that becomes relevant again when we pull all these bits of information together later on. So in the mesosphere, we've got it very cold. There's very little water and there's very low pressure. And the one thing we haven't really talked about are these particles. Again, I've got permission to use this animation. So this is a time lapse of a meteor coming into Earth's atmosphere and burning up, and you can see this little sort of ionization or vapor trail being left and being carried by the wind in those upper layers of the atmosphere. And that trail, am I allowed to call it smoke, Sandra? Meteor smoke?
Yes.
Yeah. She told me off last time. Meteor smoke. So there has to be some kind of particulate matter to make this smoke. And these particles are actually very small. Do you know what that is, Sandra?
Whoa.
It's a trick. It's not a trick question.
That looks like a hair follicle.
Yeah, it's an electron micrograph of a hair. Are you okay, Sandra?
Is it the hair?
Yeah, yeah.
I think I was losing you there. Is that the hair follicle?
Yeah, that's a hair under an electron micrograph, and this is about 80 micrometers in diameter, which is about 80,000 nanometers. And most of the particles up in this mesosphere are sort of less than 10 nanometers. So there's 8,000 particles of smoky dust in the width of that human hair. So they're very small. Now, back to history. People have observed these clouds and they're wondering what they are. They defy all sorts of logic because they're too high. They're seen after dark, after sunset, but eventually they work out that they're likely to be ice. They've worked out their altitude. And then in more recent times, we've studied the atmosphere and the gases and water vapor at these levels with rockets, with spectrographic equipment based on the Earth and also satellite based. And I'm not going to talk really any more about these things. That's the whole talk in itself. And these particles of smoke are actually acting as nuclei. The little water vapor there is condensing around the nuclei and forming droplets, which can obviously will freeze at those temperatures. Now, there isn't a lot of water at this altitude. Again, I've asked Lynn Harvey for permission to use this, and she's happy. We've got days of the year again along the x-axis. And so this is, I think I've labeled them. Oh yeah, here we go. So we've got 10th of April, 30th of April, 20th of May. And this up the side is parts per million of water. So you can see in April, you've got about 1 part per million of water, which I tasked Julian with trying to work out how many molecules this was. And we were both struggling, but Julian got there in the end, and it's actually quite a lot of water molecules, but it's a lot. It's sort of 25,000 fewer than at ground level, at sea level. So there's not a lot of water up there. And if we just look at the red plot, each of these plots are for different years going from 07 to 19. If we just look at the red one, which is the 2019 data, you can see the water content in the mesosphere increases throughout late spring and into the summer. And this coincides with the appearance of noctilucent clouds. And that makes sense because you need a bit, the more water you start to get, the more likely the clouds are to form. And we've also, in the summer, we're getting these colder temperatures, so it'll freeze and become apparent. And what Lynn's done with this data is to show, is it playing sort of rolling through? Yeah. Looking at the amount of water vapor for various latitudes going from 35 north to 80 north. And as you can see, as it rolls through these, there's actually more water vapor for any period of time, the further north you go. And I didn't actually read about why that is. Is that relevant, Sandra? Or
I'm not sure why it is either.
Okay.
That's getting
fine. So that's it. We're in the mesosphere. We've got our nuclei. We've got our water. We've got very low temperatures, and so we can form this ice and form noctilucent clouds. So now we've got to do some celestial mechanics. It's all go in this talk tonight. There'll be questions at the end. So here we've got an image of the Earth spinning on its axis, and that's not right because the angle's wrong. The Earth's actually spinning at an angle like that. And if we look at the Earth in its orbit, this is the sun. The Earth takes a year to go around the sun, but it stays in this angle with respect to the sun. So I can't remember if I've labeled the next slide. Yes, I have. So here we've got northern winter on the right. So where's England? UK there. So the UK is pointing away from the sun in northern winter. And so obviously the sun will look low from the horizon. And then in northern summer on the opposite side, so 100 and whatever half of 365 is, half a year, 6 months later, the UK is pointing towards the sun. So the sun's going to be higher above the horizon. And then in the spring and autumn, it's sort of halfway. So what I've done here is imagine the horizon is, instead of being round around us, we've straightened it out. I'm going to call this the James Dawson projection. It's very hit and miss. The Dawson Brantingham projection.
Oh, sounds like a line in America.
So you can imagine there you're looking north, and then you've got east and south behind you and west to your left, but I've straightened this all out. So what happens at the spring equinox is the sun rises due east, and it's highest when it's due south, and then it'll set due west. So that's the spring equinox. Now, the summer solstice, with the sun at its, I can't remember what the definition of the summer solstice is. The
solstice means standing still. It's at its highest point.
That's right. So the sun is rising somewhere between north and east. Again, it reaches its highest points when it's due south, and it sets between west and north. And then we go to the autumn equinox, which just is a mirror of the spring. And then the winter solstice is the sun is rising between east and south, highest due south, and then sets between south and west. And what we need to remember is this is just the sun above the horizon. So if we think about the sun, what happens when it goes below the horizon, these curves aren't very good. My PowerPoint skills were going to pot at this point. So when the sun sets in spring, it's going down, and it's reaching its lowest point below the horizon when it's due north, and then it comes back up for the morning, and then it starts again. And at the equinox, it's 37, the maximum height's 37. This is for us in Nottingham, 37 above the horizon, and the deepest depression of the sun is 37 below. Now in the summer, the sun spends sort of 2/3 of its time above the horizon, so the scale is a bit to pot here, but its highest is 60 degrees above, and its lowest depression in Nottingham again is 13 degrees below when it's due north. And then we've got the autumn equinox again, and then in the winter it's spending much less time above the horizon and a greater proportion below. So why are they only observed between May and August, and an hour after sunset to an hour before sunrise? So more illustrations. So here we've got Julian, our chairman, standing on the earth, and it's daytime, the sun's above, and it's night on the other side of the globe. And then 12 hours later, Julian's standing out there cold because it's dark, and in Australia or wherever opposite us is nice and sunny. So if we imagine, here's Julian again, and the black line is now the horizon. So we can't see below the horizon, although we know there's stuff there. We just can't see it, and the clouds are above his head. And so we can shade out below the horizon because that's just not visible. And then what happens at night is Julian's in night, and the clouds above him have all gone dark because they're not being illuminated by the sun. But you can actually see there are patches here where the sun is shooting past the Earth, and Julian's oblivious to it because there's no particles in space there which are interacting with that. The moon would fall into here, and the International Space Station, as it orbits, would transiently go through one of these areas, be illuminated. That Julian, I pointed at the screen and you can't all see that, sorry. The ISS will come through here, Julian will see it brighten up as it hits the sunlight, and then it'll go back into the shade again, and it will vanish. And then it could technically do the same the other side. And if we've got atmospheric clouds over here, they're not illuminated because they're not in sun. And if they're below the horizon, well, they're below the horizon, so we can't see them anyway. But if we had some clouds out here, very high up, they would be illuminated. And this is where the noctilucent clouds are forming, in this very high region, which are catching this sunlight passing the Earth, and they shine up, and Julian can see them in the distance. And that is why we can see noctilucent clouds when the sun sets. And there's actually a specific period of time. So the sun needs to be sort of 6 to 16 degrees below the horizon. And the exact numbers, there's different sort of arguments about what the exact numbers are, but above 6, it's likely the sky is to be too bright and you won't see them. And if the sun's much lower, then this angle changes and they'll be below the horizon and you just won't see them anyway. And generally this amount of depression of the sun below the horizon in the summer, when we've got these perfect conditions, is generally an hour or so after sunset. This is midsummer's day, and an hour before sunrise. Right, how are we doing for time? Oh, not bad. So I thought we should show some images. There's been a lot of theory, and so Dane kindly sent me some pictures he'd taken from Knowlton earlier this month. And here you can see some lovely formations of the noctilucent clouds, again low over the horizon.
If you look at the left bit, where just move your pointer slightly to the left and up, you see that rippling sound? That's exactly what was described in that letter.
Yeah,
that's that headphone effect.
Yeah,
and normally it's curved slightly, but yes. So that's as soon as you start seeing that sort of stuff, you know you've got noctilucent clouds. That and the color steel grey.
Yeah. Now most people, in fact, is there there's another one of Dane's here. There's often a bright star in pictures when people take noctilucent clouds. Yeah. So
Capella, the patron saint of noctilucent cloud watchers.
Yeah. So Capella every summer, sort of about midnight or so, is pretty much due north, low on the horizon. And so if you can see these sort of steely blue clouds and there's a bright star, or you know it's Capella, and it's, again, for us in Nottingham, the clouds are generally below Capella. I don't know about for you, Sandra, further north.
Yes, well, right now, yes, but as it gets denser, I've seen the clouds directly overhead here.
Right.
So, and you never know, you might get that at your time, because when they were seen in Italy, certainly there were people your area reporting them up to 60, 70 degrees.
Okay. Here we've got another picture. This is from John Hurst from Eastleek, 3 a.m. I can't imagine Maureen was impressed with him leaning out the bedroom window. Maybe she was holding his legs. So
John, one of the funniest one of the funny things I get is reports from people who, although they don't stay up, have, shall we say, slight bladder problems in the middle of the night. And, oh, well, have a look out the window and, oh my God, there's Noctilucent Clouds.
Yeah.
The amount of reports I get like that is amazing.
Now, John's also, this is from last year. You can see on the far right, there's a comet. So he got Neowise as well. So he's got Neowise and the Noctilucent Clouds. That's one of mine from Cotgrave. That was again from 2019. And that was from last year. And Neowise again is over here.
That's a beauty. And again, you can see right in the middle there, that sort of ripply sand effect.
Yeah.
That sort of effect. It's a classic.
Yeah. And you can see the atmospheric clouds in the foreground dark because they're too low to be illuminated. And then here's one from Lee, from Cotgrave, again from last year. Again, we've got this rippling effect, steely blue. And one from Brian Lilly from 07, I found on the website. If you're out there, Brian, I hope you don't mind.
The other thing, if you notice, they almost look like jet trails. So that's another bit of a clue. Sometimes all I see through the clouds is what I think is a single jet trail, and it's actually Noctilucent Clouds. And then the clouds clear, and I see the whole thing.
Yeah. And again, a bright star, so that's likely to be Capella.
That would be Capella, definitely.
And Brian here must have been a good display because they're coming up well above Capella.
Yeah, that I would say up to about 30 degrees.
Right, and then I've got another video. Again, this chap Goran Strand, he's in Sweden. He's a photographer, and he's allowed me to use this animation or time-lapse video with an all-sky cameras of some Noctilucent cloud progression. So this is sort of a 360-degree view over a couple of hours. And you can see over that period of time, the clouds are moving. And because they're so high, you can't really tell that they're moving so rapidly, but they are moving very quickly. Have you done many time lapse of Noctilucent Clouds yourself, Sandra?
I don't go in for time lapse, but some of them do. There's a guy in Canada. He's got tons of the stuff. I mean, masses.
Yeah.
And there's another guy up at the top of Scotland. He does that as well. He does the time lapse. The interesting thing about the time lapse is you can actually see the speed of them, and it actually takes. There's what they call a polar vortex, and it takes about 5 days to go round. So I'll tell you a bit more later on the satellite side of it.
That's it. So that's a look at Noctilucent Clouds. Some of the background behind it, hopefully to whet people's appetites to get out there and look for them when it's clear. Certainly, I don't think tonight, unless it rapidly clears. They're relatively easy to photograph, and Sandra would love your observations of them.
Yes, please. Just a quick one.
Yeah.
If anybody looks at space weather, do you go on the internet and look at space weather?
Yeah.
If you do, look on the left-hand side and go down, and you'll see just below a picture of the sun and showing coronal holes is a picture of Noctilucent Clouds, what we call polar daisies. These are taken by the Ames satellite, and that looks at ice in the mesosphere. They're about 2 to 3 days old, but if you see a lump sticking out about 2 to 3 days ago, and just work roughly about 80 degrees per jump, then you can have a guess at where it is. Is that, did you have space weather up there? Did you?
Let me put that up. let me do a new share. Where's space weather?
Right.
Is it?
Funnily enough, you've got the.
Is it on?
But go down. Just go down the left. Just no. Go. Keep going down. Keep going down. Keep going down. Keep going. Keep going. Keep going further. Bit further. Bit further. Bit further. Right. Oh, stop. Go back. It's jumped. You've gone past it. Up a bit. Up a bit. That's it. Hold it there. See that one on the left?
Yeah.
That's it. And if you click on that, you can get a full screen view as well. There you go.
So what's this showing us?
Basically, that's showing you Noctilucent Clouds. If you take the pointer and point it down to the bottom, just come down a bit further and then up a bit. Move up and then just fraction to the right. There you go. That's the lowest part. So that's at about, what, 65 north. You can normally see about 10 degrees. So that should be visible from about 55 north. So UK, that would go down to central England, central northern Germany, Denmark, Sweden, everywhere. And this is it expanding, and as time goes on, it'll get bigger and bigger. So we could see it go much further.
So this is the 14th. So it's a couple of days ago.
Yeah, it's normally 2 to 3 days behind.
Yeah.
So what I'd guess is if you take your pointer and move it to the top, just up right, I would say that is where we are now. So that will be overhead now, because it all rotates clockwise and it takes about 5 days to do a complete circle.
Right.
That's the polar vortex.
Ooh, fascinating.
There you go. And you can see why they call it daisies, because there's gaps out the side as well.
Yeah. Got a picture here of some Noctilucent Clouds.
Yes, the other thing is they'll tell you if somebody gets a sighting, they put it up quite quickly. So
Right, that's good. So if you've got any questions for Sandra or for Jeremy about the Nova, get them in while we've got them both here. And Richard, you can probably take control back. And we've got Julian to also ask some clever questions about the Nova.
I was just going to ask a quick one. So it's generally north you've got to look for Noctilucent Clouds, is that right?
yes.
So you need a good north horizon, which is unusual in astronomy.
Yes, you do. Having said that, they do go quite to quite a height. So maybe about, you can strike lucky. The other thing is, because they're lit by the sun, they're much brighter than the aurora. You can normally, on a modern camera, you can do it on automatic settings. I like to go to manual, but you can, and people have taken pictures with iPhones, the latest iPhones, no problem at all of these. So they are bright.
Richard, have we got any questions on the chat?
Fred wondering if the ripples in the Noctilucent Clouds are gravity waves.
I hate that term. Myself and Ken Kennedy, yes, the scientists sometimes call them gravity waves. They're actually pressure waves moving up and down. But yes, we reckon that's what the cause is. It's not really gravity waves, is it? Really, it's more the movement of the atmosphere. So
yeah, I think so.
Yeah, pressure waves.
Yeah. Pressure waves, yes, but yeah, and the more we get satellite information tied in with ground observations, the more we get to know about it and the movement. Most of this stuff that I'm talking about now has been cracked within the last 5 to 10 years about its movement and things. And also the Ames satellite has a habit of going US. That means unserviceable in military jargon. So we're then back to square one and relying on observers' reports. So
Well, I was going to say, if it was a detection of gravity waves, they'd have wasted a fortune at LIGO.
yes, very true.
Sandra,
They are beautiful.
With the solar wind impacting on the exosphere, does that have an impact on satellites? Because presumably the density up there must change.
Yes, very much so, and it causes them great panic. You've got to use more fuel to sort them out. If it gets too dense, they'll actually start crashing down. So, yes, by and large, the sun's quite quiet at the moment, but everybody's a bit worried when it winds up again as to what will happen, and precious. So they're constantly watching space weather, if you like, to keep an eye on the satellites. And I'm just looking at some of the questions. Yes, they are beautiful, and not only that, unlike the aurora, which people have difficulty seeing sometimes, and sometimes seeing different colors, this looks spectacular. It really does. It's almost an electric blue color, and it really looks nice. If you've seen them as far as due east, I had a view last night, about 4 nights ago, where they went virtually from due east to due west and to a height of about 35 degrees. So they were absolutely spectacular. But that's not the best I've seen them. I've actually seen them overhead. There is a catch out on this for me. As you noticed, they're seen below 6 and 12 degrees, between 6 and 16 degrees. You can be seeing them down there, and I am still too high above the horizon because I'm at 57.5 north. What's your latitude? About what, 52 is it?
Yeah.
Yeah. So you will see them, and it'll take the sun to set another further 5 degrees before I see them. So quite often on June the 21st, I get a phone call from somebody in London saying, "We've got Noctilucent Clouds down here." And I said, "Right, I'll put out a thing, but it's still too light up here." If you remember it from where I am, on the 21st, the sun only gets to 9 degrees below the horizon. So
I've got a quick one for Jeremy, if you're still there.
Yeah, I'm still here, Julian.
So this particular nova seemed to decay very, very rapidly. Is that like unheard of, or is that?
Yeah, it really is unprecedented. I've been trying to find out the rates of other novae, and I think the fastest until now was one back in 1975, Nova Cygni 75, which was a bright nova. I didn't actually see it myself, but that faded within a handful of days. I can't remember the precise number now, but there are fast novae, medium novae, and slow novae. And fast novae is anything that decays 3 magnitudes in less than 24 days. Well, this particular one is 3 magnitudes in just over 2 days. So it really is very, very fast. And yeah, people don't really know why. I haven't seen a lot of other reports. I think the spectra will probably reveal something. All I've seen is that the spectra are changing very, very quickly, as well as the brightness. So I mean, perhaps I can show you. I mentioned the other nova that's around at the moment. I don't know whether I can show you the light curve of the other nova. I'm just trying to share my screen now. Can you see that?
Yep.
So I've just pulled this up. This is from the BAA variable star section photometry database. So this is the light curve of Nova Cassiopeia, which erupted in the middle of March. And this is a funny one because it erupted to about magnitude 7.7 and pretty much stayed there until late April. So a month it was constant. And then it decided to rise a little bit gently. And then over a couple of weeks, it went really bright. So it became naked eye. Some people actually saw it naked eye, and then it faded again, and then it slowly rose. The last week it faded, and it just seems to be brightening again. And this is now 3 months after the eruption. So this is a slow nova. And one of the things that is known is that slow novae, as well as giving in the eruption, putting out a lot of hydrogen, there's also a lot of dusty material. So this is dust that's moving around in the vicinity of the binary star. So two extremes of novae at the moment: a really fast one and a lethargically slow one.
Oh, very good. There's a couple more questions in the chat on novae. So John says, novae don't have to be binaries, do they? Question mark.
Yeah, but novae, all novae are binaries. Supernovae don't have to be. Some supernovae are, but other ones aren't. There are different classes of supernovae.
Yep. And Fred says, do novae eclipse behind their donor star?
So yeah, so you can get eclipsing novae. You don't normally see them eclipsing actually during the nova explosion itself, because there's so much bright material out there. But when they're faint, if that binary star is in, if one star is rotating around the other in our line of sight, then you will get eclipses. And that's great when that happens, because you can measure the orbital period very accurately from the time between each eclipse.
Oh, very good. Thank you very much. Oh, yeah, I'd just like to say thank you very much for both of you for agreeing to appear on this installment. Get that in there quick.
Pleasure.
Any more questions?
I've got one there, Robert. But how do you know they're not stratospheric clouds illuminated from underneath? Right, you've got to be careful with this. First, it's the timing. Always check, and you can do this with any of the star programs, that the sun is 6 degrees below the horizon. That's the first thing. So if you're looking just after sunset, no, it probably is. So that'll give you darkness. The next thing, look where the moon is. If you've got the dark of the moon, fine. If you've got moonlight, yes, you can get stratospheric illuminated from underneath by the moon, but it's a different sort of color and it doesn't look like that. Having said that, you can also have a cloudy sky, and it's sometimes very difficult when you've got very, very weak noctilucent clouds to do it. So basically I take photographs anyway, just to see how the color comes out, because that confirms it. But normally those two things, i.e. make sure the timing's right. If you can see a star, i.e. Capella, you know it's probably dark enough. So those are the sort of things you have to look for.
Question from Stuart Portis. Jeremy, is the frequency of double stars known, and does it vary with masses?
I think, if I remember correctly, the majority of stars actually occur in double or multiple systems. But what is unusual about the double star, the binary star in a nova, is the fact that both systems are at a particular stage of their evolution. So one of the stars is very old, so it's come towards the end of its life and ended up in a white dwarf, and the other one is a younger star. So the time over which that situation exists is relatively short in the life of a star. So they do come and go.
And how rare is that nova that we've just seen? What sort of, is there a return period for these types of events?
Yeah, well, that's a really good question, Richard. So in terms of a given star, a given nova, how often will that go off? Well, it's thought that eventually all novae will recur at some stage or another, because the eruption, as I said, doesn't destroy the double star. It only blows off a small fraction of the hydrogen. So when all that gas clears, it will settle down into its normal rotation and continue as it was for maybe 1,000 years, 10,000 years, or even longer. But there are some novae that have been observed to go off more than once, and these are called the recurrent novae. And the shortest of those is actually a nova that I've been following for the last few years in the Andromeda galaxy. So it's not in our galaxy, but it's bright enough when it goes into eruption to see in my back garden telescope. And that goes off about once a year.
Oh.
So recurrent novae are really quite common. There are one that's worth keeping an eye on is called T Corona Borealis, which goes off around every 80 years or so. And the last time I think was in 1946, probably. So we're due for another one of those. So every time I go out in the evening, I have a glance up at Boötes to see whether perhaps with my binoculars to see whether T has gone into nova outburst again. I think we've seen 3 of those have been recorded.
Cool. One from Lee. Does the donor star illuminate ionized nova ejector, or is it luminous from its own original energy?
Yeah, so the 2 sources of the major illumination. So the brightest of all, which causes this 14 magnitude outburst, is indeed the thermonuclear heating of that hydrogen that's blown away into space. The other source, so when that dies down, is do you remember the white dwarf was drawing hydrogen off the donor star, and it goes through this accretion disk. So that's the next brightest part of this system.
Okay, one from Tony Hancock. Will the spectrographic data that you showed us allow us to tell if the dust which is causing the rapid decay?
Yeah, so the spectra will show what molecules are present, and if there is dust, and I haven't seen any dust in this one in Hercules, but in other novae they have been seen, you'll see heavy elements in the spectrum, and that's the telltale giveaway.
Cool. And it's from Fred. Do recurrent novae eventually go to type 1?
Yeah, probably they do. They probably turn into supernovae at some stage. I don't know. I don't know whether anybody knows whether they all do that, but they could well be precursors of type 1A supernovae.
Post that in the live chats if anyone knows. Do we know any details on the mechanism that caused the Cassiopeia nova? That's from Rob Bush.
Sorry, it just broke up on that one.
Sorry, do we know any details of the mechanism that caused the Cassiopeia nova?
Yeah, so it would be the same mechanism. So basically, the hydrogen piles onto the white dwarf, and when there's so much or too much, there's the pressure becomes so high that you get a nuclear bomb essentially, and that blows it up. And eventually, through several cycles, the white dwarf will get more massive and more massive. So as I said, it's not all blown off each time, so it will accumulate. And then when the white dwarf itself gets to a particular...
Cool, thank you for that. I think we're stealing James's thunder. He wants to ask Sandra a question. He's still on the line. So.
Sandra, when I was thinking, isn't it typical the blinking Nova people get all the questions?
It's all right.
So when I was reading about Noctilucent Clouds and reports of the BAA section, they were reporting most often the most southerly extent of shows of different years. Why do you think the clouds are becoming more evident further south, nearer the equator?
This is the $1 million question. Right. There could be several reasons. They're quoting climate change, global warming, pollution from rockets, The meteorite fall is about standard, so that's probably not it. But people are very, very worried, especially the climate specialists, and they're watching all sorts of bits, especially the Noctilucent Clouds. At one stage, if you remember, scientists used to think that the atmosphere stopped at the top of the troposphere, and we didn't have to worry about it. We now know that the whole thing is interlinked from the sun all the way down to the surface of the planet. And if you mess around with any part of it, you're going to get problems. So what they're doing is watching it. That's why the observations are important. What is really causing it, we don't know. It's shall we say, cutting edge. That's why we're trying to watch it as much as we can. We do know that prior to the 1800s, it wasn't seen at all. So we do know that it's a very pristine area, if you like. It's like Arctic tundra, and once you leave a mark there, it stays there for a long time. Beyond that, that's about the level of knowledge we have at the moment. That's why they put the AIM satellite up there to make sure we can monitor it. In fact, I don't know if anybody was watching, but when they went down south, it was very, very late in starting. And the reason being their circulation there didn't circulate properly for some reason. So the Noctilucent Cloud, instead of starting at about mid-November, didn't kick off until about, I think, the 7th of December or something like that. So it does give us a warning of the large circulations, and El Nino I think was involved with that one.
Right,
how much meteor dust is in the upper atmosphere on average? I don't know. I really don't know. They reckon, and I've seen so many different figures, they reckon about 200 tons of meteorites fall on the planet every year. But I've seen so many different figures on that, so I think they're still guessing on that one. Also, don't forget that rockets go up through the atmosphere. In fact, some of the classic pictures on space weather of rockets forming Noctilucent clouds as they take off. So we know that, and the space shuttle dumped lots and lots of water. That was the biggest one. Nuclear bombs, did it affect? I have no idea. However, you saw the effect of the volcanic blast and the shove up effect. So yes, possibly. What happens is, although the nuclear blast won't get to the top, what it does is push the whole atmospheric column up. And if it pushes damp stratospheric air into the mesosphere, as soon as it gets into the mesosphere, it will rise because it's colder. So it's highly possible, but I've got no data on that at all. Don't have World War III, otherwise you'll have lots of Noctilucent clouds. But that'll be the least of our worries.
So there's a question there about, for me, why Nova Cassiopeia is fading more slowly, and that's so that one of the reasons why novae fade quicker or slower is how much heat was generated in the nova explosion or eruption in the first place, and how quickly it dissipates, how quickly the gas flows out. So in Nova Hercules, it's going out very, very quickly, and eventually there will be a shell, a gas shell around the star, which could well be a planetary nebula. James, I didn't see the eruption in 1946. Thanks for asking that. But I think what tonight's discussion has shown is that it's worth continuing astronomy during the summer months. I know so many people. I was having a discussion with a Scottish fellow the other day. He says, "Well, it doesn't get dark up here, so I just pack my kit away and don't do anything for 2 or 3 months." Which is so disappointing, because there's a lot going on. There's the Noctilucent clouds that James and Sandra have been telling us about. They're wonderful. Get out there and observe them. Yeah, it might not be so good for looking at faint, fuzzy, deep sky objects. There are probably better times of the year for doing that. But there is other stuff. There are the novae that are around. And of course, the planets are around as well at the moment. I've seen some great drawings and images of Jupiter and Saturn, and even of Venus now, which is just making its appearance again in the evening sky. So I don't think there's any excuse for packing away or just staying indoors or having barbecues or whatever. Get out there and observe.
Definitely, and it's a lot warmer, isn't it? I think the
Absolutely.
The nights we had about this time last year, wasn't it, with NEOWISE and the Noctilucent Clouds, were some of the best astronomy nights ever. So,
yeah.
Shame it wasn't sunny for the eclipse earlier in the week. Never mind. Cool. Well, I think we'll probably wrap it up there. We've had quite a few questions coming through. So thanks all for all your inputs this evening and preparing the talks. It's been really good. Lots to keep on top of. Hope everyone followed the questions at the end, but yeah, it was really enjoyable evening. So thank you everyone for doing those talks and staying on to ask the questions this evening. I did just put some links to Jeremy's article on the live chat, so hopefully people can follow those up. So that's the BAA page that Jeremy's written on the NOVA. So if you want to have a look at that, and you can see some of the graphs that are in Jeremy's slides, do log on to the BAA website, and I think it's linked there from the homepage. So
and James Dawson has liked it even. I see that. Thank you, James.
Yeah, encourage you all to submit observations if you get any over the coming weeks. Right, any more from anyone else? No? Good. Once again, thank you so much for all your time preparing those talks, and it takes a lot of time and effort to put those together, so that's hugely appreciated. Next meeting then, so our next main meeting on Thursday the 1st of July, it's on the JUICE mission. We welcome back Dr. Chris Arridge. That's going to be online again on our YouTube channel, so that should be quite interesting to see what's coming up with that JUICE probe. I think it's going to Ganymede, if I'm not mistaken. Is that correct?
Flyby, I think.
Yeah, so that should be quite interesting to hear all about that. Then our next social practical astronomy, it's probably more practical, isn't it, on YouTube meetings, Thursday the 15th of July. I don't know if we've decided what that's going to be on. We'll see. Any thoughts, James?
I was going to delegate that one to Julian.
Okay. You've done a lot of work tonight. We'll let you off. Yeah. So that's
stay tuned for the next practical one.
That's the meeting in a month's time. And then I think we're hopefully going to go ahead with the barbecue on Saturday, the 7th of August at the observatory. So we really welcome you all to come up there. Hopefully restrictions will be all lifted there and we can do that as planned. It'll be outdoors.
Drink and be merry.
Yeah. So hopefully that will be the NAS members reunion at the observatory. So more details will be posted out about that nearer the time. So yeah, I think that's it for tonight. Thanks to Jeremy, James, Sandra, and Julian. So we'll see you on the 1st of July. Until then, from all of us here, good night.
Thank you very much to our guests.
Thank you very much. It's been a great pleasure to be with you.
Good night.
Bye-bye.
Thoroughly enjoyed it. Cheers.